Hey, so I'm going to show you an algebraic way to compute the area element in polar coordinates. Because the book talked about doing these polar rectangles, and through kind of a hand wavy argument, the book ends up getting that dA equals r dr d theta. And it's also it was kind of hard for me to read, at least. So I'm gonna tell you another way to do it. Actually, I think I might do two ways. So the first way is to plug polar coordinates into dx dy. And for those of you who know a little more math, this is called using the differential forms. But we don't need to go into that here. It's the algorithm to do it is quite straightforward, because we know that x equals r cosine theta, y equals r sine theta. So then we just plug these two things into dx dy. So dx is you just apply d to everything. So dr, I'm going to put c equal to cosine theta because it'll make it easier to read, hopefully, than very long expressions. So dr times c, that's cosine theta, and then minus r s sine theta d theta. And similarly, dy will be dr times s plus r cosine theta d theta. Remember, derivative of sine is cosine. Derivative of cosine is negative sine. Okay, so now we just plug these two things into dx dy. So dx dy equals drc minus rs d theta times something similar looking, drs plus rc d theta. So now we expand, but let's just you need to note something, that dr d theta, we're not going to treat this as d theta dr. In fact, we'll put a minus sign, but let's just wait for that. Let's just FOIL it out. So we get dr squared cs, and I'm going to look for the d theta squared term next. So d theta squared, let's multiply the last ones. So we have r squared sc. In fact, there's a negative sign here. Okay, now we have the important terms. So all these first terms, we're eventually going to set those to 0. So let's get that out of the way. So now the cross terms. So we have, the first is negative rs d theta drs, and then we have the other cross terms, which are plus drc rc d theta. And we can just simplify that out a little bit. This is minus r s squared d theta dr plus r c squared dr d theta. You can tell that if there's a c squared and an s squared, there's probably going to be 1 somewhere if everything is good in this world. So here's where we use that minus sign that I talked about earlier. So what we'll do is we drop the dr squared and d theta squared terms, because certainly there is none of these square terms in the area element. So that should make it plausible that these are not allowed. So we'll set those to 0, and then b, we're going to replace d theta dr with minus dr d theta. So this is, so dr d theta, it has the plus orientation. You don't need to know what this means, but there's a good reason we're doing what we're doing. But if you just follow the rules that switching the d's gives you a minus sign, you end up getting the right answer. So let's do it. So afterwards, we get r, because now we have a plus sign, s squared plus r c squared times dr d theta. And that, of course, is r dr d theta. That is exactly what we wanted. So there wasn't any of this hocus pocus Riemann sum stuff you had to deal with here. You just plug and chug. There's also another way. So this, I call this the differential forms way. But you could do this a second way too, which is actually, I think it might be slightly easier. Again, if you like the books, Stewart's books, Riemann some way, you can do that too. That's fine. I'm just trying to present alternatives. So you can do it also using the line element. So the line element ds squared, if you recall from single variable calculus, an arc length, it has a horizontal component and a vertical component, and it's the sum of these things. So if you start with the line element, you again just plug polar into it, and then b, you take the square root of the coefficient product. So for example, in Cartesian, it's just 1 times 1. So you get 1, and then this is the thing in front of dr d theta. So d coordinate 1, d coordinate 2. And this will be dx dy in the Cartesian case. So the volume element looks like this. So in the polar case, what it'll end up looking like is r squared times 1 dr d theta, which will end up giving you r dr d theta. So let's just show you why the line element gives you r squared. So if you take dx, we know from before it is cdr minus rs d theta, and dy is sdr plus rc d theta. So now, if we plug it in, we end up getting cdr minus rs d theta squared plus sdr plus rc d theta squared. So the key thing is the cross terms will cancel. See, what ends up happening is if you FOIL each expression out, we get c squared dr squared plus r squared s squared d theta squared. Those are the good terms. And I'll just keep writing good terms. So s squared dr squared, that's the second expression, plus r squared c squared d theta squared. So now we have all the good terms. Now here's the bad terms. It turns out the bad terms are good terms because they also cross out. So c dr, and we put a negative sign, rs d theta, and I'm going to put a 2 here because in line element land, we're going to allow dr d theta equal to d theta dr. Don't ask me why. The reason why is kind of like, it's kind of technical, but if you just follow the rules, it'll work. And it kind of makes sense, right? Like, there's no orientation for arc length. That's really what's coming down to here. So now the second cross term, plus 2 S dr times RC d theta. So now let's just count what we have here. We have a d theta, we have a d theta. We have an S, we have an S. We have a dr, we have a dr. We have an R, we have an R. And there's a C, and of course they have 2. And so that minus sign is what kills these cross terms. So we end up getting, if we collect each coefficient, c squared plus s squared, all in front of a dr squared, plus an r squared s squared plus an r squared c squared in front of a d theta squared. So that gives us finally dr squared plus r squared d theta squared. In particular, there's a 1 here. So now what goes in front of the dr d theta, the volume, or the area element, is the square root of 1 times r squared, according to this definition right here. So that means, so I'm claiming that dA is this thing. And that is totally right, of course, because that's just r. Okay, so this is just another way to explain where polar coordinates comes from. And let me just make one more remark. Dimensions. If you ever study physics, you'll know that dimensions are one of the most important things to keep track of. It's a bookkeeping device that lets you avoid mistakes. So the key thing is that theta has no dimensions. It's just a number. Really, it's in radians, right? And that's because we can plug theta into sine. Sine of 2 meters cubed, that is not a thing. You cannot do that. But you can do sine of 2.5 radians, for example. That is an okay thing to evaluate. If you've taken single variable calculus and you study Taylor series, you know that sine of theta is theta minus 1/6 theta cubed and so on. And these things, they're just numbers, right? So that just explains, I'm just trying to explain why theta is just a number. It is not, it has no units. So if we tried dA equals dr d theta, this has dimensions of meters. This has no dimensions. So that means that would say that area is measured in meters. That is so wrong, right? It's meters squared. So that means you need to add an r, meters. So just the usual dimension heuristic checking allowed us to see why we need that extra r. Okay, that's all for this video.